the last lecture, we will discuss about our second example of design of plate cutter in which there is a we have to provided a vertical stiffeners. Okay, so students, what is the difference between example number 1 and example number 2? So, the basic difference between example number 1 and example number 2 is in example number 1, it is clearly mentioned that you have to design for unstiffened plate girders. Okay, so unstiffened means there is no any stiffeners are provided while you have to design for plate girder. Okay, only end post or end stiffeners are provided. Now, in the second example, it is clearly mentioned that you have to design for a transverse stiffeners only. It means you have to design a plate girder in such a way that you have to provide it the intermediate end stiffeners, which is your vertical stiffeners. Okay, so students, you can see that there is no data, no any change in our data, and we will continue our example number 2 like this. So you can see that our question is design a welded plate cutter for a simply supported deck span having a load which is subjected on 24-meter span is 20 kilonewton per meter, which is your dead load, and this dead load is our excluding self weight. Okay, so first of all we have to find out self weight of plate girder. After finding out the self weight of plate girder, next we have to find out factor load which is subjected on 24-meter spans, and this factor load will be calculated and the drawing will be like this. After our first step, next step is to find out maximum bending moment and shear force generated. Okay, so students, this is just a revision of our example number 1. So as per data given, our maximum shear force and bending moment will remain same because the span is remain same, the load is also remain same as per our example number 1. So our maximum shear force and bending moment is 996 kilonewton and 5976 kilonewton into meter respectively. Okay. After our second step, next step is section selection. It means we have to select a section in such a way that it restrain a maximum shear force of 996 kilonewton and maximum bending moment of 5976 kilonewton into meter. Now the main difference between the example number 1 and example number 2 is described in our step number 3, which is section selection. So whenever we have to select a section, then this is our plate girder section in which there is main two components. This is our flange component and this is our wave component. Okay, so first of all we have to find out the size of wave plate. So our size of wave plate is, this is small d. Small d means optimum depth and this is thickness of wave. Okay, so whenever we have to find out optimum depth of girder, then the equation of small d is mk by fy raised to 1 by 3, in which we have to provide it capital M. It means maximum bending moment for which we have to design, and it is 5976 into 10 raised to 6 into k. Now, this k is our coefficient based on whether you have to provided any stiffener or not. So, it is already discussed that there is three types of example in this chapter. First, there is no any stiffeners are provided. So, for that case, we have to put down the value of k is 150. When any transverse stiffeners are provided, then we have to put down the value of k. The value of k is 180. Generally, it is in the range of 180 to 220. And when it is clarification given on the question that you have to design a plate girder for as well as horizontal stiffeners, then you have to take the value of K is equal to 250. Okay, so students, the major difference between all these examples is in the value of K. Okay, so in the last lecture we have to cover up to step number 4. Okay, in which you can see that this is a revision, and in the last lecture our size of plate girder is, this is our flange portion, orange color is our flange portion. So the area of this portion is, this is width of flange, and it is find out as 500 mm. This is thickness of flange and it is 40 mm. This is optimum depth of girder and it is 1500 mm. This is thickness of web portion, it is assumed as 8 mm, and this flange portion is remain similar as this flange portion. So this size is 500 cross 40 mm. Okay, so our overall depth, our total depth of section is 1580 mm. Okay, so students, let us check our selected section. This is our trial and error section, having a size of flange is 500 cross 40 mm, and the size of weight is 1500 into at 8 mm, is take maximum bending moment which is 5976 and maximum shear force which is 996 mm, sorry, 996 kilonewton. So it is feasible or not to provide it this section. Okay, so let us check our step number 5, which is check for moment capacity. Now, check for moment capacity means our selected section takes maximum moment or not. Okay, so let us start. First of all, it is already discussed that in our last chapter, which is design of gantry girder, in which our flange portion takes bending moment while our wave portion takes shear force. Okay, so let us check our provided flange portion restrain maximum bending moment or not. So first of all we have to check our selected section is in which state, is in which class. So generally there is four class. First class is plastic, compact, semi compact and slender. Okay, so we have to derive the class from page number 18. So you all the students are moved to page number 18, in which there is a first line. It is written as outstanding element of compression flange. For that you can see that the value B by TF. Now what is B? B means the width of flange divided by 2. This clarification is given on page number 19, in which there is a first figure. Okay, so our width of flange is 500 mm, therefore your value of B is BF by 2, so it is 250 divided by 40, so it will give answer 6.25. Now this 6.25 is less than 8.4 epsilon. It means your selected section is in plastic class. Okay, so as per plastic class, let us check our selected section takes how much moment. So students, for bending moment check, you can see that your equation will be like this. It is MD is equal to beta B ZP Fy by gamma M0, in which your beta B is equal to 1, because it is clearly mentioned that you have to take beta B is equal to 1 for plastic and compact section. Next, Fy. Fy means yield stress. So it is generally always 250 megapascal, or it is also called as 250 Newton per mm square. And your gamma m0 is partial safety factor, which is 1.10. Now only term is Zp. Now as described the value of Zp in our example number 1, let us check our Zp is A1Y1 plus A2Y2 plus A3Y3. This equation is derived in our chapter number 7, which is plastic design. Okay. Now we have three members, 1, 2 and 3. So A1, it means area of first member, it is 500 cross 40 into Y1. Y1 means whole section, I section CG, and only first portion CG's difference is called as Y1. So it is 770 plus A2Y2. Now this I section is a symmetric section, and for symmetric section the wave portion CG and the combined CG is exactly at the same point, and therefore your value of Y2 is 0. If your y2 is 0, then a2 y2 terms is also 0. So it is directly written as 0 over here. Now a3 y3. So a3 is 500 cross 40 into y3. There will be typing mistake. This a3 is also 770. Okay. So students, as per data given and as per our calculation, our value of ZP is 30.80 into 10 raised to 6. Okay. Now if we are putting the value of ZB into this equation, it will give our answer 7000 kilonewton into meter. It means our selected section is safe against moment. Okay. Now same calculation is for shear. Now what is the equation for shear? The equation of shear is given on page number 59, and it is Vd is equal to AVFy by root 3 into gamma m0, in which root 3 is constant, gamma m0 is 1.10, Fy is 250. Now what is AV? So you can see that AV is shear area, and the equation of shear area is given on the page number 59, and there is two types of sections are there. First is rolled section, which is ready-made section available in the market, and second one is welded section. So for welded section, we have to provide a welded plate girder over here. So for welded section, our shear area is D into DW. Okay, now what is the value of D? It is 1500 into TW. It means thickness of wave. So it is 8 mm, which is assumed. You can also assume the thickness of wave is 8 mm or 10 mm or 12 mm, whatever. Okay, basically it is in the range of 8 to 12 mm. So students, after putting all this value, we will get our answer 1575 kilonewton. Now, this is not your final answer. You can see that over here on page number 53. Your VD is multiplied with 0.6. This V does not exceed 0.6 VD. So we have to check 0.6 VD. So if we are multiplying this value with 0.6, then you can see that our answer is less than our maximum shear force. Okay, it means our wave portion which resists shear force is doesn't capable to resist a maximum shear force. That's why we have to need a provided of intermediate stiffeners. Okay, so students, this is the end of our step number 6. Now last step. Our last step is wave buckling check. So students, this is not in your these examples. Okay, so you have to not see this typing. Okay, so students, our last step is wave buckling check. So it is already discussed that for wave buckling check, there is two methods are there. First one is simple post critical method, and second one is tension field method. So whenever there is no any clarification regarding, you have to provide it or you have to design a welded plate girder using simple post critical method or tension field method, then for simplified method is a simple post critical method, and that's why you have to use simple post critical method. Now for simple post critical method, you all the students are moved to page number 60, in which the equation is given as VCR is equal to AB into tau B. Now AV means shear area, which is already taken as D into TW. Now, what is tau B? So you can see that on page number 60, your value of tau B is depend on the value of lambda W. Now, what is lambda W? And you can see that your value of lambda W is depend on the value of tau CR. So, for tau CR, the equation is kV into pi square into E divided by 12 into d by tw whole square into 1 minus mu square. But your d is 1500, tw is 8 mm over here, 1 is constant, mu is Poisson's ratio and it is 0.33, sorry 0.3, 12 is constant, E is modulus of elasticity and it is 2 into 10 raised to 5. Pi is 3.14 or it is also called as 22 by 7. Now what is kV? So you can see that on this page the kV is given as 5.35 when transfer stiffeners are provided on at least on and the supports. Okay, it means if there is no intermediate or no vertical or horizontal stiffeners are provided, then you have to take the value of kV directly as 5.35, which is given and which is already done in our example number 1. Now whenever you have to provide it intermediate stiffener, vertical stiffeners, then first of all you have to check what is the ratio of C by D. Now what is D? D means 1500 and C means spacing of transfer stiffener. So first of all we have to assume that our C by D ratio is 1.3. Okay, because this condition will be assumed in our step number 4. So for that condition you can see that if we have to make a subject of C, it is 1.3 into D. So our C is 1950 mm. So therefore our round figure value is 2000 mm. Okay, now 2000 is our provided value. So our actual provided C by D ratio is 1.33, which is less than 1.5. It means we have to satisfy our assumption which is made in our step number 4. You can see that this is our assumption made in step number 4. Okay, so now our last step in which we have to check our C by D ratio is 1.33, which is greater or equal to 1. So our equation of kV is 5.35 plus 4 divided by C by D ratio, which is 1.33 whole square. So students, after putting the value of kV is 7.61, E is equal to 2 into 10 raised to 5, D is equal to 1500, TW is 8 mm and Poisson's ratio is 0.3, and after putting all this value we will get our answer of tau CR is equal to 39.12 Newton per mm square. Now if we have the value of tau CR, it is obviously we have the value of lambda W, and after putting the value of tau CR in this equation we will get our answer of lambda W is 1.92, which is greater than or equal to 1.2. So for greater or equal to 1.2 we have to provided the value of tau B is FYW divided by root 3 lambda W square, and if we are putting the value of lambda W is 1.92 in this equation, we will get our answer of tau B and this Taube's answer is provided into this equation, and we will get our answer. VCR is 469.8 kilonewton, which is much lesser than our maximum shear force. Okay, so students, this is the reason why we are provided intermediate stiffeners. Okay, so this is the end of our step number 7. Now it is already discussed that in our last lecture, in our last example, then whenever we have to provide intermediate or transfer stiffener, then and only you have to provide it, and you have to check for anchor force. Okay, anchor force means the force which is restrained by the stiffeners. So the anchor force equation is given on page number 62. So you all the students are moved to page number 62, in which the equation of reaction, which is shear force, is HQ by 2. Now what is HQ? So you can see that HQ means 1.25 into VP. Now what is VP? 1.25 is constant. VP is given in just below equation. It is D into T into Fy by root 3, in which our value of small d is 1500. Our value of T is 8 mm. Our value of Fy is 250 divided by root 3. So we will get our answer of Vp, and we have to provide it into this equation. 1 is constant. VCR. So VCR is 469.8, and Vp is find out from this equation. So we will get our answer of HQ, and if we are provided the answer of HQ, then it is HQ by 2, and it is 924.6 kilonewton. Okay, so students, this HQ is greater is less than our 1575. So 1575 is find out in step number 6. Okay, so we will pass. So therefore the end panel is safe to carry a longitudinal force. Okay, now similarly MTF, it means moment resisted by the intermediate stiffener, and equation is very simple. HQ is already find out in this equation. D is 1500 divided by 10. So we will get our answer 277.38 kilonewton into meter. It means this moment is taken by our intermediate stiffeners. Okay, so this is the advantage of why we have to provide it stiffeners on some distance. Okay, so students, this is the end of our today's session, as well as our chapter number 4, which is design of plate girder. Now we are not revise our example number 3, in which we have to provide it vertical as well as horizontal stiffeners, because the difference is the value of K. Okay, so students, this is the end of our today's session. Thank you.